Hi everybody, I'm Banchan and I come from the Department of Computer Science, Texas University, USA. And today I'm going to present my research solving advection reactions diffusion PDE with QNN quantum networks, PIN physics informed networks. So first, I want to discuss about the motivation. So quantum computing with its unique properties, superposition, entanglement, inference, enable algorithms such as Groover's and Shaw's with clear superiority over classical counterparts like classical counterparts. Meanwhile, networks underpin deep learning and now power many leading technology trends. One of the most potent application is physics-informed networks. Someone calls it short is PIN. It's an effective solver for nonlinear and highly stiff partial differential equations. The intersection use quantum physics-informed networks, or stand for QPINs, exploiting the strengths of both the solver PDEs more efficiently. The next one I want to discuss is the gap hypothesis and the contribution. We start from the gap. Although QPIN solvers with VQC stands for variational quantum circuit, at the core perform relatively well versus PIN. The still embedding remains one of the primary obstacles hindering quantum advantage. Prior work shows us using network to learn the VQC parameters before encoding improve QPIN performance. So it means we can use a tradable embedding. Embedding is one of the most difficult problem in quantum area, and it relates to the input and output. So we start from the we start with the hypothesis. Applying a quantum networks to learn these parameters will further improve the learning capability of the VQC, similar to what classical neural networks achieve. And beyond that, we did a contribution. We introduced a framework, a model. We call it QNN QPIN, stand for quantum networks, quantum physics informed networks. It's a hybrid quantum classical PD solver. At the moment, we are in the NISQ era in quantum, so it's not easy to have a fully quantum version. So we utilize hybrid quantum classical with the quantum learnable embedding. We evaluated our research on the 3 case studies: heat, reaction division, and never stop equations. It's increased from the easiest equation to the hardest equation. Let's talk a little bit about the physics-informed networks. It's a classical version classical version of solver. So a feed-forward network takes inputs x, y, t. In here, x, y is space, and t is a time variable, temporal variable, and predicts solution variables. So here, for example, we have the function u, v, p. For example, u is like velocity, or p like pressure. In the solver, we use automatic differentiation, computes the derivatives used in the loss. You can see here in the right, we can calculate the loss from the model, from the input data. We have loss from PD, loss from boundary condition, stand for BC, and loss from the initial condition. So we combine all three loss here to have the model learn the data. We try to reduce the loss. So here, if we look at the equation number 2, lots of PDE will be between the predicted from the model and from the solution. And the boundary condition here, we have 2 terms. The first one, the first one here first one here is the term it belongs to the condition derived, and the second term is the condition Newman. And if we have the combine of the two terms with the coefficient alpha and beta, we can have some other like a Robin boundary condition. Depend on the equation, we can have some sort of boundary condition like that. For the equation number 4 here, you can see it's a loss of initial condition, and we can have the initial condition, the loss condition based on the true value based on the derivative. Okay, now move on to quantum version. So assuming scientists are using quantum physics informed networks to solve the PD. So QPIN is an extension of PIN into quantum environments. Instead of using classical networks or like tensor networks in classical version, it's used variational quantum circuits or called Stanford VQC to approximate PD solutions. So in the right slide here, you can see is a quantum circuit VQC with multiple layers. The input will be transformed from classical data. In here we have a 4 qubits, and the classical data will be transformed into hidden space by the embedding. And at the end, we have the measurement here to convert back from the quantum state to classical data. So if we can see in the equation number 5, VQC includes multiple layers. So each layer here, we call it, for example, UL, is function, unitary function, UL of theta. Theta is parameters that will be used to learn is the frequency. And in equation 6, you can see it's a product multiply of the Hermitian H here is Hermitian operator, and W here is unitary transform. That means VQC will be the transformation of multiple layers, quantum gate, and qubits. So it will transform the quantum state inside the VQC, and we can house the quantum circuit to learn from the input data. In here, we learn from collocation points is collocation point is the grades of the equation. Now I move on. Our contribution here, we apply the tunable embedding because in some previous research, scientists propose that embedding is problem specific, but in here we try to prove that embedding is problem agnostic, so we can use the tunable embedding and have the quantum, the qubits can learn better than before. So input here as grid scale via a file map onto the domain -1 to 1 to balance the magnitude of spatial and temporal variables. Each qubit is encoded by a rotation angle from the feature map. So there are multiple ways of embedding from classical data into quantum states, like computation basis or and so on. But here we choose the rotation angle because by using this one, it's easier for the model to learn the parameter. The equation here, the equation here shows the embedding, the tunable embedding, and we use the quantum gate, rotation gate as the y-axis, and we transform and using the rescale coefficient here, phi i's. And here it has two input variable is phi x, thinner and temporal time, temporal T there. So our architecture utilizes the tunable embedding concepts, but replace the UMB with quantum networks to learn the embedding parameters in parallel with the main VQC. So on the right is the quantum circuits about our model. It also have 2 layers and 4 qubits. So here is the overall architecture of our proposed solution Q and QP. You can see the input here will be the collocation points with initial condition, the inner points, and the boundary. The input here will be the input data will be inputted to the quantum circuits and transformed in the Hilbert space, and we compute the loss. Here we use 3 loss. Depending on the equation, we can have only 3 loss or maybe 2 or 3 loss. And then after that, we use a classical optimizer here, LBGRS, to optimize the parameter. So here is training algorithm. We initialize embedding parameters, theta and rational parameters, theta embedding and theta VQC, theta value, and normalize to the domain -1 to 1. And we compute embedding angle phi, prepare the encoded state, apply the rational circuits, and evaluate predicted fields. And then we calculate loss. Here we have 2 coefficients, lambda j and lambda ic for the boundary condition and initial condition. The coefficient will have to balance the loss to avoid overfitting of the model. So for the gradient to both parameter theta embedding and theta VQC of the both with the optimizer LBFGS. And then finally we repeat until converge and save the train parameter and the model. For the hardware, training is run on classical simulators because there's a problem of the quantum computer now. We can't have a fully quantum computer to train our model, so we chose the solution to train the model on classical simulators. And for hardware, we use the RePath supercomputer at Texas University with the NVIDIA's core CPUs. Each node would have a 4 core 8100 NVL, and which train on classical computers which entirely feasible for systems with fewer than 20 qubits. So it's limitation for the classical computer because for each node we increase the number of quantum bit, qubits more than 20 it will be class. So if we want to have more than 20 qubits, we need to run parallel. For the software, we use classical version. We use PyTorch from Facebook for the classical optimizers, and for quantum version, we use PennyLane. It's a quantum machine learning library. Circuit using here, we use single qubit division with 3 gates, X, Y, and RZ. But for the embedding, we use RY. And of course, we need the C0 entanglement gates to utilize the quantum phenomenon. Special phenomenon is entanglement. For benchmarking our solution, we use 3 case study. For the first case study, we use the heat equation. So for here in the equation number 7 is the heat equation with the 2 terms. The first one is derivative of U with the variable t, and the second term is the Laplacian second derivative, and is applied in the domain t belongs to from 0 to 0.95, and for space we chose the space in domain from -1 to 1. For the boundary condition, we chose the relay because it's smooth for the head equation, and for the initial condition, we use the function u 0x equal to c size px. It means the value will be choose with the truth value. For the pin, is some result from our experiment. for the pin, it's saturated at 22 pulse with just steep loss. You can see in the right slide. For the Q&Q pin, it declines steadily and smoothly over 100 pulse, still capable for the learning. Because heat equation is a parabolic linear, so it's so easy to solve. And in here, pin sound a little bit better than Q pin, but Q and Q pin have potential because you can see in the form as a function. And here you can see on the right is the heat map to show the solution between the pin and Q pin with the reference solution. For the different solution here, we use classical solver RK45 to find the solution and compare it with our model. In the second case study 2, reaction diffusion equation is more stiff, and nonlinear equation in PD. So in here we have to solve two equation, number 8 and number 9. So you can see here for equation is more stiff because it have the multiply bit it has a square of the activator. So here we have a two function, activator and substrate, and you can see here for C squares is a term of nonlinear. So it's difficult. So in difficult PDE, here we also choose the domain T from 0 to 0.95 with two condition directly and double bump. In here we chose double bump, and you can see here our model show state of the art and better than pin with the loss lower than pin in total and in two function activator A and substrate S. We train with 200 pulse, 4 qubits, and 10 layer VPC, and 5 layer for the embedding QNN. The last one, for the case study 2, you can see here QNN pin dominated pin in all the pulse. Here we compare with 100, 150, 200, and 250, and QNN pin also shows the SOTA in comparison with pin. In case study 3, we use the most difficult PTEs, Navier-Stokes equation, with 3 equations, 10, 11, and 12. Here, the first two equation is the momentum equation, and the last one is conservation law equation. So for here, the Q-pin, so the better results and both baseline. We chose the Chebyshev Q-pin as the Q-pin baseline, and we compare with pin. So QN Q-pin shows the better solution with very low loss here in both function, pressure, and velocity. So it means with the more difficult equation, nonlinear equation, so QN Q-pin show the better results than others model. We also have inference and to chase overfitting. So here we have the prediction of U and P, velocity and pressure, and you can see here with the function U, the heat map shows the totally map between the model solution and the reference solution. For the pressure, only some abnormal here. You can see the dot here shows the difference between our solution and the classical solution. In conclusion, we introduced Q-pins that use quantum network to learn the rotation angle parameters as the main variation of quantum circuit. Across the 3 case study, Q-pin achieves a superior loss with low value and consistent smooth relation with our simulation. And our model learns effectively and show no signs of overfitting, providing smoother solutions than conventional classical methods. So it's so some limitation and future outlook. So we will continue to enhance our model to tackle more complex nonlinear PDE, and we also try to solve the problem behind plateau phenomenon in our model. Thank you for your attention.